Good morning and welcome to the effective outage management through advanced fault detection and isolation techniques. My name is Ahmed Musa. I'm the Utility of the Future Manager at PHNG, and I'm the CEO and founder for Electric Bridge Consulting and the 100% Energy Club. I've also been fortunate to sit on several boards, and I'm currently an adjunct professor at NJIT. So I have worked for 4 utilities so far. Have been through many events, storms, disasters, first-time events. So I'll share with you kind of a lot of the lessons learned. So the agenda for today, really focusing on smart sensors, machine learning. What could we do to prevent? I would say we cannot really prevent Mother Nature from attacking, but how can we mitigate the outages by reducing the impact, increasing the reliability for the customers, enabling faster backup power? What could you do for microgrids and so forth? So actually increasing the reliability and resiliency, if you will. So as you see from this picture, when there's a storm in the horizon, and unfortunately in the US, we're always bombarded by storms, the forecast is very poor. It's really, really poor. So from a system operations perspective, we break down system operation by the day. A blue sky day, which everything is perfectly fine, gray sky, kind of local outages, black sky, major events, and so forth. And then recently, there've been a lot of records that we're breaking. Basically, the strongest storm, the tornadoes, wildfires, earthquakes, volcanoes, you name it. So the grid is being severely attacked, and the utility have a lot of responsibilities to prepare the system, for the next event and so forth. So a lot of us are focused on climate change. I'm not here to convince you if climate change is real or not, but one thing for a fact, the weather is changing. So even on the normal blue sky day now, which used to be like a very easy day for utilities, we have to perform certain operations if it's a sunny day or if it's a cloudy day, especially as we transition towards 100% clean energy future and 100% renewable energy future. We rely a lot on the weather for the solar availability, the wind availability, and so forth. So what's really interesting from a storm or any kind of weather event, I created this critical path 5W to address the storm forecast and actual damage. The first W is when, where, what, who, when. When will it hit? The time. Where will it hit? The physical location. What will it damage? The actual damage expected. Who will support from the utility, mutual aid, and others, and most importantly for the customer, when will they be back? Depending on the answers to all these W's, you could start the microgrids, you could, charge your batteries and so forth to be ready. Now, I'm a big fan of ML and AI, but what's really interesting is, I always think of 2 simple questions. What machines are we going to choose to educate? Which are the critical assets? And what is the intelligence that you want them to learn? And notice I mentioned intelligence because intelligence basically is the ability for you to think outside the box, to come up with creative ways. From that perspective, we have a lot of data in the utility. A lot of it is unsupervised. So how can we provide all this data input to be able to answer the 5 W's in a more efficient, more reliable manner? And again, the best example in New Jersey, we had a 100% clean energy goal by 2050, and the governor advanced it by 2035. So we're moving the light speed to come. So we have to really utilize all the available tools to have a reliable and a resilient system. So from any issue, basically, there's an input. Let's say the data we have, whether it's weather data, telemetry from SCADA from the field, or so forth. There's some assumptions how the system is going to behave in the next event. There are theories based on all the information that we have. And then finally, the output. The output could be the modeling output versus the actual output. And then we could compare the model results with the actual event results, and then basically calibrate and edit and redo the next time. As far as data, we got a lot of sources of data, the power plants, the step-up transformer, the transmission and distribution systems, the substations. And lately, we've been adding a lot of fast-acting devices, like in this case, a StatCom, which is an electronic device that provides data every 2 cycles or so. So we're talking about a tremendous amount of data on a per second level. And then as you come close to the customer, AMI meter used to be the last point. We have a lot of data come from the meter, but recently there's been a lot of activities, a lot of investment behind the meter. So now we're going the next level to the customer: solar, storage, electric vehicle, and so forth. So we have a lot of intellect coming from the field that we could utilize. So renewables, distributed energy resources, that's like very, very critical for us. So depending on where you're physically located, the most important data point is the solar irradiance. It tells you a lot, how great it is, how poor it is. The picture you look in front of you and the bottom left, this graph, that was the solar output for a day. Of course, it looks terrible. And that's kind of a sign of some utilities, especially in the East Coast and other locations, they're really struggling because the performance of solar is very poor, as you can see, which results in the top right, the voltage profile at the solar site, and the bottom right, that's the feeder where the solar site is connected to. So the idea here is that again, we're talking about sensors, we're talking about intelligence, better outage management. The weather plays a big role, not just during the actual event, but post-event and the day before or 2 days before the event. Do you have enough to charge the batteries and so forth? Speaking of batteries, here's a picture of the 1 megawatt frequency market battery. The ancillary service. There's been a lot of activities in this field. Again, the difference between solar and battery, they both generate. Solar is a function of the weather, of course, the availability of the sunlight, but solar does not need to be charged. But the battery, it's a load and it's a generation. So again, the idea here is that if we're able to optimize the output that we have, we're able to optimize the battery to mitigate the next event and so forth. But as I mentioned before, the forecast has been terrible, at least here in the US. For some reason this year, the last year, it's actually getting worse instead of getting better. Even on an hourly scale, you check the weather app and it tells you, for example, it's perfectly fine. You look outside, it's raining. So something is really happening. And that's kind of interesting. You can see from the picture, this funny picture. It goes from rainy to sunny to storms to extremely hot to like unhealthy conditions. So why the recent focus on outage management? Really, right? That's a very important point. I gave a lot of discussions before, a lot of presentation about this topic, and there's always something new. In this case, it's very important because you're probably familiar with, don't put all your eggs in one basket. We are putting everything in the electric baskets. Literally everything. Our transportation, electric vehicles, not. Of course, even the heat in some areas, building electrification. So whether it's cooling, the AC, or with heating, the heat pumps and so forth, it's all the transportation sector. It's even the future, planes, buses. So if there's a massive event, massive blackout, the system would completely shut down. So that's kind of the importance of a discussion like this to find ways to mitigate. Events will happen, faults will occur, but we're trying to minimize the damage as a result. And here's a best example. The picture in the bottom left, when Superstorm Sandy, for example, hit the East Coast in 2012, there were a lot of buses, there were diesel buses, so they're able to, help the commuters. But nowadays, a lot of the bus depots are electrifying. We're talking about the evacuation, right? From impacted hospitals and so forth. Picture in the top left, right now there's a big focus to electrify the airplanes, and the bottom right, that's an electric boat. So again, all methods of transportation are becoming electric. And then in the US, I strongly recommend you guys to read about FERC Order 2222. Very simply, pretty much everybody and anybody could participate. So, it's your home and your business. They could install solar, storage, fuel cells, demand response, and so forth. They could do all the stuff and participate. So now imagine, instead of just relying on a nuclear plant or fossil fuel plant, now the system is relying at your house and your business. So can you imagine the amount of data points and how complex that is going to be? And then, as I mentioned before, we try our best to minimize the damage. But again, we cannot control the birds, we cannot control all the animals, the balloons, people, drunk driving and hitting like a pole. But there's some stuff we can do. But here, I love this picture because I work in asset management, and asset management basically have an asset and you're managing this asset. So the most important or the critical function for all utilities is to maintain and improve safety. So this picture kind of says it all. This is one thing you want to avoid at all costs. You don't want to avoid having to make the call or having any fatalities or even any harm to your employees, contractors, people around the station, wildlife, and so forth. So safety is very, very important for us. The next is, when event does occur, like in this case, you can see a picture of a couple of substation transformer fire. Again, you have a lot of thousands of gallons of oil, so this can last a while. So many of us are trying to identify ways to prevent this from happening. And if it does happen, to very quickly isolate that location. So from sensors, which we're discussing today, we're adding a lot of sensors, a lot of monitoring equipment to a lot of transformers to minimize an event like this from occurring. Storms, again, just imagine all of a sudden there's debris flying around because of the wind, category 1, 2, 3, 4, or 5, and the damage that's going to result. So we're installing sensors, we're installing infrared cameras, we're installing HD cameras at different substations to be able to bring back some intellect, such that if you're an operator, all of a sudden you get all these alarms and you're trying to make sense of it. It's system is smart enough to pick up, or something happened at the station. Here's a live feed, then the operator would know right away what just happened. Floods, I mean, that's happening on a global scale, especially in the US. We've been getting a lot of floods. Just putting the sandbags around or this balloon, like it's not really going to work anymore. The amount of rain is unbelievable that we're seeing. Also, if you do something like the picture in the top left, and then it rains a lot, you basically created like a swimming pool, and the electric system is technically not waterproof. So again, from an outage perspective, we are installing weather stations, flood sensors, and so forth. And then as far as renewables, they are not immune from this. I'd like to make this point very clear. Renewables are immune if they are designed to withstand very aggressive storms, for example. So the picture in the bottom right, you can see the storm went through the solar farm, pretty much destroyed almost 85% of the farm. The picture in the top left, there was a mini tsunami, and the floating solar panels landed on top of one another. Because of the mutual heating, they started a fire. The pictures here, again, there was a storm, I believe that was in Puerto Rico in the top right. On the picture on the left, there was an internal fault in the middle row, and you can see all the panels got damaged. Pictures in the bottom right, it's a wind turbine during a storm, and the braking system failed. So the point very quickly here, by showing you a lot of different slides, is that the entire system really is kind of vulnerable, and we're only as good as our design compared to the expected event. Since, like I mentioned in the beginning of the call, we're getting a lot of first-time events. That means the system was not designed properly to withstand such an event. So microgrids has been getting a lot of popularity, especially ever since Superstorm Sandy, like 10 or 12 years ago. So microgrids, basically, why do we need them? Well, when the system is down. So if you have a local interruption, whether it's a gray sky day or a major black sky day, or the system is already underground, basically the transmission system shut down, you can't get gas and stuff like that. Like the system is completely damaged, then you're able to start up the microgrid. So microgrid simply is the ability for a customer or multiple customers to disconnect from the grid to supply their own power under major events. And also nowadays, they have the ability to do the same function while connected in parallel to the grid. So we're seeing a lot of applications now for microgrid, and the less reliable the utility is, the more likely microgrids will play a bigger role. So here's two pictures, the top left and the bottom right. Basically, as you could see, let's start with the bottom right. Before, you had a wind turbine, which is not very common, but the solar are common. Battery, you could see the load. The control is very important, but in this case, you could see like a natural gas-fired generator or a backup diesel generator. The picture in the top left, you don't see any natural gas resources because there's a big push in some states, including New York, not to rely on natural gas resources. So again, instead, you got electric vehicles, vehicle to grid, you got energy market, and so forth. So again, It's just worth mentioning that from an outage perspective, the discussion we're having today with the sensors, sometimes you make the decision that it's time to fire up the microgrid. The other point that is getting more popularity, and again, it does relate to our discussion today, is the idea of smart cities. So smart cities started with a smart street light. You replace the LED, you put a controller and so forth, but there's a lot more steps you could do. There's a lot of sensors you could install from an ESG perspective, from the weather perspective, and so forth. Then you go from the street light to the city itself. You increase the intelligence of the city by adding more sensors. And we know that we operate, the blue, black, gray sky day. And then ever since COVID hit and people were able to work from home, a lot of cities have been trying to attract, residents and businesses by, having this whole, my city is better than your city. But in reality, the ultimate goal is my city is more reliable and resilient than your city. Because if you're going to move to a place, you need to have reliable power and reliable internet. So again, the microgrid I mentioned before, depending on the regulatory requirements and the rules, this stuff may vary, but most likely most of them now at least are proposing solar storage and some vehicle to microgrid, V2M. Some of them that if you don't have an issue with natural gas, they expect fuel cells, CHPs, and so forth. Again, it's very unlikely to have like wind turbine part of a microgrid, but communication is very important and the backup is very important, right? Remember, the microgrid, a lot of it is designed for doomsday scenario. So the last thing you need is to spend all this money to have a microgrid, and when it's time to operate the microgrid, the communication system fails or the control does not perform as expected. And nowadays, a lot of developers, they would like the utility to operate the microgrid for them. So a couple of, you could see this video is already old, it's over 2 years ago, but there was a title called "What Happened to the World the Last Week in July." That was the first time I saw this, but then when I kept going back, it was the last week of July, the first week of August, second week of August. So you kind of get the point that every day almost there's an ongoing event. So from that perspective, we're not here to discuss how we could mitigate climate change impact. We're here to discuss how can we increase the intellect of the system such that in the next event, we're able to reduce the number of customers out, we're able to bring them back very quick. So the journey for us in the US, at least, safety was always number one. Number two, we had a couple of blackouts. Again, and there was a lot of, you could see here from the picture, there's lootings, there was, safety incidents. So electricity is kind of very closely tied to the safety of people. And then all three was the last blackout that happened. So this is, again, one of the other pictures we're trying to avoid. So utilities have something called OMS, the Outage Management System. So what we're talking about today, since I manage the utility of the future, is what is the ideal OMS? So we are investing in an ADMS, which is an Advanced Distribution Management System. But really, like the ideal situation here is to avoid outages. Remember, if you follow an IEEE 1547, that should have said 1547 2018 version. We now have a lot of options that we have to abide by, because the IEEE 1547 2018, it provides information about the right-through. So how would the DRs perform under high voltage, low voltage, high frequency, low frequency, faults, and so forth. So can we make use of all this available inverters to reduce the number of customers out? What is our goal? Our safety, Kiri, are we going all the way to zero? What's our target? How are we going to address outages in the future for 100% clean and renewable energy when all the baseload generation have been retired a while back? So DERMS could help, DERMS could hurt the reliability of the grid. That's why it's very important to plan properly for that. Microgrids, they could help. Again, minimize the number of customers out, which would be great for us. So during COVID, when people lost power, basically life stopped, because first of all, they work from home, their kids go to school from home. Home was their everything. So when the Wi-Fi is down, when the internet was down, when they lost power, the internet was down, no hotspots. Sometimes the cell phone communication was interrupted depending on the scale of the outages. You couldn't relax, you couldn't watch Netflix, you couldn't watch YouTube. Schools were out, so the kids were going crazy at home. Again, if it was a very hot day, you can't use the AC and vice versa, and so forth. So the idea here is that life as we know it stops. But like on a serious note, really, power outages, other than just the loss of power itself and the loss of sense of safety, you lose communication as well. And then that's a problem because you have a critical customer, they're going to be negatively impacted, which is a pretty, very important deal. As you can see here, some of the list of the customers. Then moving on. Again, when COVID hit, there was a hurricane called Isaias that hit like the New York area, the New York metro area. And a lot of customers, that was their first storm in COVID. They weren't very happy with the loss of power. Even if the loss of power lasted like, a couple of minutes, they were kind of questioning how come we do not have wireless transmission and so forth. It's really kind of interesting really because that basically kind of shuts down the utility function if you have like wireless, or why don't we bury everything? They don't want to see any assets all underground, which again is ideal, but it's kind of cost prohibitive if you will. So the question is, can we prevent failures? I personally don't think the answer is yes, because there are birds, there are kids still with balloons, there are people who drive drunk, there are just mistakes. Like you see, there's a lot of what if scenarios that happen. What you could do is have a better communication, better system protection, better settings, faster kind of reconfiguration of the grid, and so forth. Again, like I said, machine learning and AI, I expect to play a big role in this as well. At the end of the day, if you remember the last W, a lot of customers, they kind of understand, they appreciate what the utility is doing. But what they need to know is when are they going to come back? Because if it's going to be like a long duration outage, they could go get a hotel or go somewhere else. The problem is they're not very happy when the utilities don't provide them upfront with the expected time frame. But I think the 5W, the last one, was very, very essential because the more they know about, again, when the power is coming back, the more they could reorganize their lives. So again, just to highlight stuff like this, we're doing a lot of work. We have asset lifecycle program. We are adding intelligent equipment to the substation. We're putting monitoring, temperature monitoring, and so forth, a better fire extinguishing system. So we're spending a lot of money, a lot of investment to prevent stuff like this from happening. Same thing for here. All the sensors, all the intelligence we're adding, we are addressing them all in a more reliable and resilient manner. The flood sensors that I mentioned, that's like only step one. The cameras we're adding step two. In some areas, we're putting like submersible transformers and stuff like that. Now, depending on the actual scale of the impact, the picture you see here, I mean, this is the only picture I have, but it's kind of clear in a way that the end of the substation is already on fire. So having a fire at this massive transmission station, that's a big deal. You could see how big the station is, because that could be one of the critical components that would shut down like in the whole system. Number one, if the fire is going to destroy the station, remember we have a big issue now with the supply chain, right? Transformers usually take a year to 2 years to build. Now it's even longer. So examples like this. So again, depending on the reason I'm bringing up wildfires, which is happening unfortunately a lot in like West Coast, because they provide a whole different venue. Like events like wildfires, volcanoes, stuff like that, you can't just focus on the 5Ws because the outage is going to be for very long. I mean, if you had a volcano at the substation, this station is gone. You have to build a new one from scratch. Other interesting stuff, like I said before, in the US, we're very famous for the balloons. Again, and the impact those balloons have on the wires. We have a lot of hit poles. You can see the picture. The person hit the pole. It's a very strong hit. The transformer basically dropped from the top. And then sometimes it's interesting stuff, like you have all those birds, a squirrel who's doing some kind of gymnastic moves, or as you can see here, the monkeys on the side. So we have to deal with a lot of stuff. So a lot of stuff is not in our hand. We cannot tell people don't drink. We cannot tell people do not enjoy the balloons in graduation. We just have to find a way to mitigate them. Sometimes it gets very interesting, right? So when I found this picture, I don't know how fast were they going for the motorcycle to fly and land on the pole, basically. Or in the other case, which is very interesting, picture on the right, that's a recloser, a device that is designed to reduce the outages and enhance system. And look at the bird nest. They chose the device that is responsible for increasing reliability to nest on. So, like I said before, so people like, you know what, it's fine. We agree with all the stuff, you know, Mother Nature's attacking, the weather's not supportive and all this nice stuff, but I have renewables. And that's kind of the picture I'm showing here. Another one is that your renewables will only help during the design phase if they are designed to withstand the basically the category. So that's kind of a very important point to note here is, you know, if the utility system gets damaged, which is a very good system, most likely the DR may get impacted unless it's designed for resilient design. Again, another picture here, you could see the storms they just went through and destroyed almost every other panel also. So sometimes it gets very important, really, right? So you could see the hail that destroyed the complete destruction of the solar farm on the top right, or the wind speed on the top left. And again, as you can see, some panels flew and landed on a busy highway. So, and you kind of get the point here. I just like to show pictures for you guys to click in. Now, to address the 5 Ws, the outage level kind of drops as you go in this picture from the left all the way to the bottom right. So the power plants are the most secure. They're the most critical. You know, a loss of a power plant may result in major issues across the network, if you will. And then you start the transmission and so forth. So again, as you look at this diagram, you know, all the way to the left, you go up and then down and so forth. All of it, you know, the stress level would, I would say, increase significantly as we approach the generating stage. So my favorite is I always say going green is great, going black is not that great. And the goal really for groups like Utility of the Future and others to attain the highest level of reliability. That's kind of the goal. At the same time, allowing more and more renewables to interconnect. So we mentioned in the agenda sensors. I mean, sensors will bring back a ton of data, but really you want to install weather stations. You want to make the most usage of the AMI meters. You really want to build a smart city, and the sensors and the telemetry and the cameras they install throughout different points. As far as renewables, DERs, basically we're being pushed by the commissioner to accommodate more and more renewables. So let's do a good job by relying on their smart inverter settings and so forth to mitigate any possible voltage issue or other issues they may have. EVs, electric vehicles, they're here to stay. A lot of people already are focusing on the next level, which is, you know, vehicle to home and so forth. You know, what's the impact on the batteries and all this analysis that we are kind of working to address. Energy storage and EVs. Again, EVs is nothing but a battery on wheels, but energy storage, whether it's behind the meter, like a Tesla wall or others, are expected to increase significantly. And then, you know, you kind of get the point, as I mentioned before, it's very critical to control the inverters. That's like the next on our to-do list, to have the ability to control inverters remotely. That way, if there's an issue, you send multiple signals or just one signal, and you're able to address the issue swiftly. And then, you know, I'm a big fan of, instead of bombarding the energy control centers with more and more function, just build a new center. I like to call it the ASO, Advanced System Operation, and let that new center be responsible for any kind of voltage issues and microgrids and EVs and so forth. So that new center is kind of like a glorified R&D that looks at stuff like that. And the reason I'm calling advanced system instead of the DSO that people use a lot, because I don't like to say distribution versus transmission. You know, we have a lot of solar in some areas, and the backfeed goes from distribution to transmission. So there's really no point to separate them. But that's kind of the system. And again, we mentioned intelligent substation. We're adding a tremendous amount of data points, alarms, maintenance, monitoring, devices at different substation locations to provide telemetry. So what are the plans once this data comes back? Otherwise, it's kind of useless and so forth. And I think the best, which a lot of utilities are doing, like the very, very first step, is to hire like a data scientist to play with the data and provide like useful information. So I'm adding the last point is, since we talk about outages, what is the outage related data? You don't need the whole SCADA system, but what impacts would have on your kind of floor, if you will. So another thing that we do is the MS, the management system. So ever since Superstorm Sandy, a lot of utilities have been investing in the DMS, DERMS, ADMS, which is distribution management system, the advanced distribution management system, and the DER management system. So the idea is that you have this software that is very capable. All the telemetry is going back to software. The software is based on your modeling and your GIS system and so forth. So the system is a great representation of reality and so forth. And then the same, utilities have been using an energy management system, EMS, for many, many years, but now there's an advanced energy management system. So let's see what this will provide and so forth. So to move a little bit faster, that's the most common substation design on a global scale. 2 transformers, each supply 2 transformers, and that's the end of it. But the reason we're having this discussion, because the system looks very complex. So you may be asking, why am I talking about all these additions when I'm talking about outage? Because when outage happens, you just interrupted everything in this picture. Solar, fuel cell, distributed generation, vehicle to grid, solar, and so forth. So that's kind of the beauty of stuff like that. A lot of those designs exist right now. As far as the next step is to connect, as you can see from here, you connect feeders together, the different substations together, and so forth. So that was like the software version of an outage management system, really like a better way to enhance the OMS through software. The other thing that's happening a lot across utilities here is the hard grid modernization. It's undergrounding some circuits. It's replacing open wire with the spacer. It's putting reclosers. It's putting, and basically a lot of infrastructures that are being done to make sure the next event we will survive. And then this is kind of good because you put a physical relay, which is a hardware installation, but you have a lot of data coming back from the hardware. So that's like the best example of the two of them working together, the hard grid modernization with the software grid modernization. So as far as the outage management team, you really need to think about the grid, not just reacting to a grid, but how can you propose a smart grid and a smarter grid, which basically learns on its own. With all these devices coming back, do I need every data points? I don't think so. Instead of installing like sensors, I'm going to rely on the transformer. And then, like I said before, inverters will play a very big role, especially with the IEEE when it becomes effective in other locations. That's not going to be like an easy drive, if you want. Now, one important point is from the asset lifecycle model, really, like trying to identify how much time do you have left for every equipment? What else can I do? From an outage perspective, what will be the impact, really? So if I have a massive outage and then I have, like I say, 30 or 40 transformers in this area, which ones is at risk? As I mentioned before, as far as AI and ML, they could help us with the forecast, definitely better forecast and the speed, intensity, and so forth. They could predict the number of tree damage, which include branches and so forth. So a better way of managing one of the biggest issues we're having, which is trees. And then, from underground system, we're talking about putting underground cameras and stuff like that. The idea is you're trying to bring back the system quickly. That's something to spend a minute on. If we cannot prevent completely the reasons for failures, we could at least have a better, faster response to the failures. So SADI, KD, MEFI, and so forth are the indicator that is being utilized to measure how many interruptions, how many customers, the duration of the customer interrupted, the duration of the momentary, and so forth. So the goal ID, it's a very, very, very difficult goal, is everything is zero. No interruptions means no failures. And if we cannot really have no failure, at least have a failure plus an action plus like a switching move. So it's kind of an all-inclusive kind of outage, if you will. And then you need to look at every component you're adding. There's definitely a school of thought that the more gadgets you add, the less reliable the system would be because you're introducing another common mode of failure. So we have to have like a lot of discussion about stuff like that. So as promised on time, I'm gonna end here. If you copy and paste this link, there's that video I did in the past to kind of talk about how much information that different control center operators they have to deal with on a regular day. So again, in closing, a lot of lessons learned from the US. We've been getting a lot of attacks, if you will, by Mother Nature and others. We are looking, again, going back to the agenda, we're looking for adding sensors, we're looking for increasing the integrity of the system by adding, I would say, more gadgets. Again, having a focus on the safety KD, are we going to go to zero? What will be the target number? Microgrids will play a much larger role as well, at least for the customer perspective. So, in closing, we have everything's on the table. Machine learning will play a massive role. And we have a lot of data, historical, failures and so forth. And really, like, towards the next event. So in the East Coast, things may have been relatively quiet, but we may get like another nasty system. So, hope that helpful. Thank you very much for listening to this. And again, in closing, just to wrap up, go back for a second. We covered. So again, at the end of all this discussion, I want you to, I'll leave you with this, like, you really need to focus on this 5 Ws, see if you want to add or remove. You need to answer this question very clearly. What machines are we talking about? And then finally, we're able to go from one phase to the others and so forth. So thank you very much. Have a great day.